All right, guys, we've made it to the last lesson of the year. We're going to talk about the Doppler effect today, and we'll conclude our astronomy unit and basically be done with Earth science for the year. So this is the last thing we're going to talk about. The Doppler effect is actually something that is a physics topic related to some chemistry as well as some physics. So it's kind of an upper level idea, but I'm going to give you the basic message behind it. So essentially, if you have any moving object that is giving off some type of waves, it's going to change the wavelength of energy as it moves. So for example, if you think about like a siren on a police car or on an ambulance or on a fire truck, or even somebody just like leaning on their horn, as they're driving down the road, you'll hear this very unique sound. It sounds like this. Okay, so obviously from that video, you hear that higher pitched sound, which then as it goes by, goes into a lower pitched sound. And that's due to the fact that the waves of sound are being compressed in the front of the vehicle and they're being stretched out behind the vehicle. So with sound, it changes the frequency by which those waves hit your ear, and therefore by changing the frequency, it actually changes the pitch and makes it sound a little bit higher or a little bit lower depending upon where you are relative to that moving vehicle. Now, if you're in the car or in that vehicle, you're not going to hear any change, okay? But the person outside of it is. And this change in frequency or wavelength of energy is known as the Doppler effect. Now, this happens with any type of wave. So even like it happens with sound, but it also happens with water, right? You can look at this picture of the swan swimming, and you know that in front of that swan, the waves are being compressed, the water is being compressed over here and then stretched out behind it. So the wavelength of energy is more frequent here and a lot less frequent over here, a lower wavelength of energy over here. Okay, and therefore the swan is moving to the right in this picture. So if you look at this picture, which is basically showing the exact same thing, we can see which way the object, the red dot, is moving. It's giving off some type of wavelength. It's being compressed on the right-hand side and stretched out on the left-hand side. Therefore, it's moving to the right. Okay? Now, this is also true with light. Sound, obviously, you can kind of hear the pitch change. With light, wavelengths of light travel through outer space in waves, and the wavelength will determine what type of light or what color light it is. And so when we have an object that is moving out outer space, we actually see a change in the wavelength of light. And so in the visible spectrum, this is on your reference table, I just zoomed in on the visible spectrum. You see the red wavelengths of light are longer, and the violet or blue wavelengths are shorter. And that's important, noticing the difference between the two of them. Long red, short blue. Now relate that to this picture here. In this picture here, if we were to describe where the short and the long wavelengths are, the longer wavelengths are over here on this left-hand side, the shorter wavelengths are over here on the right-hand side. So this would be more blue in color, and this would be more red in color. And so we can actually detect changes in the movement of objects in outer space by determining the wavelength of light that's coming back to us. We can see if it's moving away from us or moving toward us based upon the same principle of the Doppler effect. Okay? And this was first developed by a man named Edwin Hubble, who is famous for the Hubble telescope. They named after him. But he came up with this idea that things in outer space are moving away from us based upon the light that they give off, and whether it's shifted toward the red end of the spectrum or shifted to the blue end of the spectrum. And again, blue light has a higher frequency, a shorter wavelength, and red light has a longer wavelength or a lower frequency. And that's important. So what he discovered was this idea that most objects in our galaxy or around us, galaxies around us, are mostly moving away from us because they are shifted toward the red end of the spectrum, or not shifted to the blue end of the spectrum. Redshift means the object's moving away from you, just like this picture we saw before. Remember, if it's moving away from you, it's a lower pitch, longer wavelength. if it's moving toward you, it would be shifted toward the blue end of the spectrum, a shorter wavelength. And so he found out that most objects are moving away from us. So it's red shifted. And I always remember red is away because red usually means like stop and stay away from it, it's danger. Okay, that's my kind of trick for remembering that. All right, so let's go a step further with this and just talk about light in general. So if you pass light through a prism, it will refract out into all of the wavelengths of light from red all the way down to violet. And this is what happens with a rainbow. And this is actually the picture from the Dark Side of the Moon album by Pink Floyd, if you're not sure. Breathe in the air. So this is what happens with white light passing through a prism. We get a continuous spectrum. And that's important, related to some astronomy stuff. So if you take a look at this picture here, there's a lot going on here, so let me explain. So the middle picture here is an incandescent bulb. And if you were to shine a light through a prism, you would get this full spectrum of light, and you'd get the full rainbow effect. That's called a continuous spectrum. However, if you did the same thing with the sun, you don't actually get a continuous spectrum. What you get is an absorption spectrum. So let me explain. You're passing light through a cold gas. And if you think about the way the sun is set up, the core of the sun, if you could see that, it would actually be continuous spectrum. But the light from the core has to pass through the gases on the outside of the sun. And those gases are relatively cold compared to the core. And so as it passes through the hydrogen and the helium on the outside of the sun, it actually absorbs some of the wavelengths of light in those hydrogen atoms on that cold gas. Then that light finally passes through outer space. We pass it through a prism or a refraction gradient, and now we get what's called an absorption spectrum. So you see these lines, these bands on the continuous spectrum that have been absorbed by the hydrogen atoms on the sun. So any star that you see in the night sky, if you look at it through a special thing called a refraction gradient or a prism, you'll get this absorption spectrum. Now, with something like a nebula is just a hot gas, and it automatically absorbs whatever it's made out of. It's going to absorb that spectrum of light, and what we're only going to get is what's called an emission spectrum. And this is actually true with something like a neon sign. Neon, the gas, when you heat it up, energize it, it's going to produce a type of light that might be red or blue or whatever that we see with our eyes. But if you pass it through a prism, you get this special wavelength of light. Okay, so these are all elements that give off different spectrums of light. So if you look at this, hydrogen, which most stars are made out of hydrogen, has a wavelength of a red right here. It's actually called red alpha. And there's a little bit of a turquoise blue here, and then a couple other ones in the mix there. Here's some of the other ones which are interesting. Helium. You can see they're all different. They're all unique. It's kind of like the fingerprint of that element. Now, if we compare this to what we were talking about earlier, so we're looking at this absorption spectrum of hydrogen. Only these wavelengths are absorbed. Now let's talk about that in the context of the Doppler effect. A hydrogen star that is at rest is going to have these lines on here at different wavelengths. However, a star that is moving is going to be shifted toward the red end of the spectrum. Remember, moving away from us, it shifts toward the red, and if it moves toward us, it shifts toward the blue. Now, what Edwin Hubble noticed was the spectral lines, the normal spectral lines of a hydrogen atom at rest, like in his lab, were right here. However, when he looked at the objects in the sky around us, all of these spectral lines were shifted to the right-hand side, to the right end of the spectrum, or to the red end of the spectrum. So that meant that all these objects were moving away from us. And so from that, he developed this idea that means that the universe must be expanding, that everything's blowing up away from us, and all objects are moving away from us. So this idea is that most objects, most galaxies are redshifted. And so you'll often see questions about this where it says, the spectral lines from this galaxy are shifted toward the red end of the spectrum. So what does that prove? And so you don't need to know all this stuff, all this chemistry and physics stuff. What you need to know is that when things are shifted to the red end of the spectrum, that proves to us that that object is moving away from us. Remember, red, stay away. Redshift means stay, or it's moving away from us. Okay, so that's the important part of this. All right, so guys, just to finish off, there's a major concept here called the Big Bang Theory, which is kind of the astronomer's interpretation as to how everything started, everything was created through this Big Bang that happened 9 to 14 billion years ago. Everything was in one single point and then exploded outward from there, and so the universe was created in this expansion, and it's still continuing to expand currently. Now, one evidence for that is this idea of redshift, so the concept that we talked about in this video. The other evidence for this is this detection of what we call cosmic background radiation, or CBR. It's really what we could say the echo of the Big Bang, and what we detect in every point, wherever we point our detectors, we pick up this microwave radiation, which is basically an echo of that. So everything's been redshifted, and if you think about what's next after the color red, it would be infrared and then microwave. So everything's been shifted all the way down to that microwave range of the spectrum, and so we're detecting this everywhere we look. And so it's kind of our evidence for this happening and this continual expansion of the universe. So if you ever see a question on the Regents exam, or not the Regents exam, or on my exam about the Big Bang, or any questions that I might ask in my book, or anything that you're doing in review related to the Big Bang, typically the answer is going to be this cosmic background radiation idea. It's evidence for the origin of the universe, the beginning of all things. Okay, now this is a big theological debate about how things started, so we're not going to talk about that necessarily, but it's at least worth looking into. That's it for astronomy. We'll conclude it with that. And if you guys have any questions about the Doppler effect, just let me know.